Andy, thanks for that kind introduction, and very excited to be part of this very interesting and informative conference you've put together for leaders all throughout the optical industry. My name is Keith Thompson from Digital Vision Systems, a startup company in Atlanta, working with some people at Georgia Tech and also some industry partners to bring a new technology to market we call the Vision Optimizer. And in titling the talk, I thought it would be useful to give you an analogy. The purpose of the Vision Optimizer is to bring some of the innovations in your industry to the patient. And the analogy was to the last mile, but I've sort of decided to change that really to the last 10 feet. A bit of full disclosure here, I probably have the wrong degree to speak to this gathering. I am an ophthalmologist. You may wonder what an ophthalmologist is doing addressing this group. Everyone knows that ophthalmologists know nothing about the optical industry. In fact, they can't even refract. Digital Vision's fortunate to have Dean Butler, who most of you know, founder of LensCrafters, several other very successful optical businesses. So Dean recently told me that his store managers used to keep track of redos and redo rates between MDs and ODs. And Dean said, Keith, ophthalmologists had 4 times the redo rate as optometrists. And I said, no, Dean, that can't be right. Your people must have dropped a digit. It had to be 40 times worse. So that said, I want to tell you, in bringing internet innovations to consumers, we don't have to go too far back in time, a couple decades maybe, when the promise of innovations in the internet was bringing us really incredible new things. Instantaneous search, things like instantaneous search with YouTube, Google, Netflix video on demand, and Skype video conferencing. But the telecom industry faced a problem at that time. There was a bottleneck in bringing these services to the consumers. And the industry turned this problem the last mile. How do you bring these broadband services through the bottleneck to the consumer? And of course, as we all know, the industry innovated and came up with a number of solutions to these broadband technologies, and thus consumers could benefit from innovations in the internet. If you look around the optical industry, and there's really no shortage of innovations. We've got freeform lens technology now that can create a lens to 1/100th of a diopter of resolution, very accurately, reproducibly. You can tailor that lens to be worn on any angle, vertex distance, and so forth. There's a whole amazing new number of progressive addition lens technology in individualizing these lenses to patients. Coating technology continues to improve, photochromic coatings, anti-reflective, and various things to improve wearing comfort. Improvement in contact lenses continues with multifocal designs to give patients improved options to manage their presbyopia. And from my world, on the surgical side, the big innovations continue in intraocular lens technology to treat presbyopia, to manage presbyopia following cataract surgery. But like the problems that the internet faced a couple decades ago, I think the industry has an unmet a problem yet unsolved, and that is how to bring these innovations to the last 10 feet, in this case last 10 feet in the exam room, to benefit from the wonderful innovations you leaders in this industry are developing. So we think there's an impediment to the delivery of these innovations, and it's in the exam room, and it's a fairly formidable impediment. It has a lot of inertia, and it's been around a long period of time. What is that impediment? Well, I think all of you recognize what the impediment is. It's the phoropter. And not to beat up too much on the phoropter, because in my analogy, it's very much like a stethoscope. It's a remarkable system, remarkable device, lots of utility, in skilled hands can do remarkable things. But it's been around a long time, and like the stethoscope, it's got some limitations. The the phoropter itself, the exam, has some fundamental limitations. There are error-prone steps that can lead to inaccurate or suboptimal prescriptions. The lenses in the phoropter typically have 0.25 diopter resolution steps. Well, that's a whole lot less than freeform technology can provide today. Perhaps more importantly, all of these innovations that I just showed really can't be demonstrated to the patient in the exam chair. And that's a fundamental problem with the phoropter that impairs bringing innovations to patients. And I think all of you in this industry will agree an exam with a phoropter is really not a 21st century consumer experience. So the Vision Optimizer was devised to address those problems in the industry. But it didn't start out that way. And I'd like to share with you briefly the story of how the Vision Optimizer came about. And in so doing, I hope to show you how far the world has changed in the last couple of decades. My story really started with Dr. Ed Norton, who was here from New York and Cornell, who went to Miami and founded the Bascom-Palmer Eye Institute. Dr. Norton was a remarkable man, but he was very much a visionary and an innovator. Much of the work of vitreoretinal surgery was done there, and when it became time for me to consider career choices, I was interested in technology and in optics, and I thought that refractive surgery would be the next big thing in my field. Most people thought that operating on normal eyes, as we called normal eyes back then, was nuts and should be discouraged, but not Dr. Norton. He thought refractive surgery, with current changes in technology, would be a very much part of ophthalmology going forward. To show you how crude things were, back in the early 1990s, Bill Clinton was in the White House, so it really doesn't seem that long ago. But let's look back a couple decades and see what we were doing, what was state of the art in refractive surgery. If you were a -2 myope and wanted to reduce your dependence on glasses or contact lenses, your refractive surgeon would take a diamond scalpel and make these incisions in the cornea, an operation called radial keratotomy. And if you were fairly skilled and didn't drink too much coffee, you could make pretty good straight incisions. And this operation worked surprisingly well for low levels of myopia. If, however, you had some astigmatism, it didn't treat astigmatism. So surgeons, being fairly creative, reasoned that, well, if radial incisions could correct myopia, adding a couple transverse incisions would simply correct the astigmatism. And this generally worked not quite as well or as predictably as radial keratotomy. What about treating hyperopia? Well, again, surgeons were a creative bunch. They rationalized that, if radial incisions corrected myopia and transverse incisions corrected astigmatism, then certainly hexagonal incisions would correct hyperopia. This worked a whole lot less well. And some patients became overcorrected from this operation and developed, say, for example, nearsightedness again or astigmatism. What did the surgeons then try to do? Well, you can see, as you might imagine, this kind of a scenario rarely had a happy ending. So at this point in my career, I saw a really promising opportunity to become a corneal transplant surgeon, to fix these problems that were extant. Fortunately, the excimer laser was developed. Fortunately, an all-new innovation called the excimer laser was introduced, also by a New York guy named Steve Trokel, and that pretty much completely disrupted, and the ability to reshape the cornea pretty much disrupted the refractive surgery space, and incisional surgery fortunately died a very quick death. Now, in those days, back to the story of the motivation for the Vision Optimizer, the phoropter for us as refractive surgeons had a really serious problem. It didn't explain the outcomes we were attaining with laser surgery and other procedures. To give you an example of that, let me share with you a couple of outcomes from patient J.K. a 52-year-old patient, minus 2.25, who underwent excimer laser surgery. He was extremely happy. His postoperative refraction was plano, he saw 20/20 at distance, and miraculously we had cured his presbyopia. He could see the smallest print in the phone book. He was so happy he was out recruiting friends and family members, one of whom, his buddy RM, came to see us, who essentially had exactly the same preoperative status, had surgery with the same surgeon and the same laser in the same facility, but had a very different outcome. Not only was his presbyopia not cured, he couldn't drive at night. We couldn't explain these outcomes with the 4-opter. This really puzzled me, and so I had the opportunity as a research fellow to work with some very smart people from Harvard and MIT to address this problem. We developed a technology we called at that time spatially resolved refractometry. It was a patient interactive test that measured the manifest refraction at multiple points across the pupil. And what was different about this technology is not only did it measure points across the pupil, but it really assessed the patient's perception of those aberrations. It was an interactive multi-point test. Using that technology, we were now able to explain some of the funny outcomes we obtained in the early days of refractive surgery. Here, for example, is our patient JK, who was 20/20 in J1+, and his buddy RM, who didn't do so well. You can see from this spatially, when we look at the refractive properties of the eye, spatially resolved across the cornea, you can see that in patient JK, we etched a perfect progressive channel right in his cornea. Weren't we smart? Well, this technology helped a lot. It was very accurate, and we used it to devise new ablation profiles. We also used it to simulate potential visual outcomes. And this was very important because when you had a patient with higher order aberrations that you thought about correcting through some process, you needed to show the patient how much their vision could be expected to change to weigh the benefits and risk of a procedure. While this technology helped us a lot at the Emory Vision Center in Atlanta, we thought that from a commercial standpoint it had limited potential. At best, it would be yet another standalone instrument to introduce into the clinic that doctors would have to shuffle patients between, in addition to the primary vision testing task that they had to do with the 4-opter and vision chart. So we thought another device adding to and not replacing the 4-opter had limited potential. Well, sometimes innovation is inspired by looking to the past as well as looking to the future. And here, an optometric colleague of mine introduced me to a technology that he still used in his office called the Humphrey Vision Analyzer. This was a technology invented in the early 1970s by really two remarkable individuals. Luis Alvarez was a Nobel Prize winner in particle physics, and Bill Humphrey founded Humphrey Instruments, which, as all of you probably know, was subsequently sold to Zeiss. The Humphrey Vision Analyzer had two main innovations. Alvarez replaced the dozens of fixed power lenses in the 4-opter with a relatively few number of continuously variable power lenses. Humphrey's innovation was he figured out a way to relay the power of the corrective lenses through to the viewing position remotely to the patient's eyes by using a concave viewing mirror off-axis. This architecture seemed to us exactly what we needed to put our technology into a new platform that could do all vision testing of the 4-opter, but better, and add the new features that we developed that we thought would be so useful. So we integrated the SRA, the spatially resolved refractometry technology, into Humphrey's architecture, and we called this the Vision Optimizer. We built a prototype and we tested it in my clinic, and we were blown away. It not only outperformed the 4-opter, we could take patients off the street with their spectacle prescribed glasses and improved vision in over 90% of them. It provided patients a completely novel experience, and they preferred the Vision Optimizer test over the 4-Opter by a wide margin. Doctors in the community that we showed this technology to loved it, and some even gave us deposits to be first in line when it was ready. We then were very fortunate to hook up with the Georgia Tech Electro-Optical Systems Laboratory under a program called Venture Lab that provides support for emerging companies deemed to have good commercial potential. The engineers at Georgia Tech have re-engineered the Vision Optimizer, added some features that I'll show you in a minute, including dynamic eye tracking and an interactive patient control system. This device is now under construction at Georgia Tech and will enter clinical trials in a couple of months. To show you how the key components of how this works, there is a tower behind the patient, and the optics are located remotely above the patient and out of their line of sight. Images are produced with high-resolution organic light-emitting diode displays and then pass through an array of continuously variable power lenses that are under control of the system computer. As the engineers like to say, this is the wavefront modulator or wavefront generator of the system. It can impart any type of focus to that image: sphere, cylinder, and higher order aberrations. That image is then directed to a concave viewing mirror that the patient looks at during the exam, and this replaces the eye chart. The engineers at Tech added a stereoscopic eye tracking system. As you'll see on the video, allows patients to test under natural viewing conditions with normal degrees of movement, and they don't have to hold still behind a bulky 4-Opter for the exam. For near vision testing, the beam paths are directed through a near viewing plate, and there's an interactive haptic dial which allows patients to either control or interact during the test. This is a rendering of what the system looks like, and we'll now look at a quick video of the patient's viewing experience. To capture this, we mounted a camera in the position of the patient's right eye. You can see the viewing mirror here, and of course we can show eye charts, or we could test acuity by having patients read. We can show images of varying targets for the refraction and allow the patient to select the clearest image. This is a picture from the eye tracker. As you see, the patient can move about during the exam, and the system will follow them. The system knows what portion of the progressive lens is looking through, and that therefore it's possible to demonstrate not only single power corrections, but we can also demonstrate progressive designs as well. And we're not limited to just doing the optical simulation. We can basically do any type of photochromic lens, coatings, premium lens accoutrements, and so forth. We're also able to show full motion video through the real optics, so you could show patients how much better they could see at night with a new correction. So we realize this is fairly early in its development, but we thought it would be of interest to your audience. We are now we completed all of our testing in the prototype, and we are now building a fully functional system that'll be in clinical trials this spring at Georgia Tech that will have full functionalities, and we will be making with our industry partners freeform and PAL lenses and comparing those against conventional lenses produced by conventional methods. We expect to be in beta trials in the fall of this year with our ECP practices and our research partners, and then we'll complete the engineering to make production units, which should be available next year. So in summary, we think this technology will provide the industry an all-new approach to refraction that is better than the 4-opter, much more accurate. It will provide patients a completely novel experience for the vision exam. And we believe in skilled hands it will be very much by bringing these innovations the last mile to the patient, a profit-generating tool for your industry. Thank you for your time.